So we wanted to make sure you're aware of something in the library. It's kind of cool, and Larry Toops will talk to it a little bit. Go ahead, Larry.
Oh, yeah. Okay, while the other cats are coming in here, we're herding them up. I just wanted to let you know the last 2 weeks at LPI here, I've been hosting 26 students in industrial design, fourth-year students from Sweden, and giving them the context of a Mars mission, a future human mission. So we have a display of their posters in the library here. And at your leisure, if you have that, you're welcome to come by and take a look at the work. It gives you some really cool insights on people who are not scientists or not engineers, what their impressions of going to Mars. And these will be developed as projects over the next few months. Thanks.
Okay, two other things. One, just a reminder, if you have an interest in going to see The Martian tonight, get in touch with Andrea so we can get you on the list. We'll get you the cost of that. Secondly, for everyone that's online, we will have an email address that you can use, and we'll have it up on the screen here, and we'll start putting it up here every time we're not showing a presentation, that will actually give you a way of asking questions online, because your involvement is really key as well. And then thirdly, you may have gathered we have different people coming up. All of these people that are representatives of our steering committee, so they're like doing different sessions. I've had just a tremendous privilege and honor of working with a really fun group of people, and so we're sort of splitting the work up in terms of prepping these things. So Marianne Bobskill, who is just a blast to work with. Marianne, who's going to take this session and run it, and then I'll take care of the Q&A part. Marianne, it's all yours.
So we have 4 papers in this session. We're going to be moving to Meridiani and then also Untitled Crater. I just would like to remind folks I'll be sitting right there, so I'll be watching. And when you have 5 minutes left, I'll go like this, and then after that I'll start to dance in my seat, whatever. So, and then again, we'll save all the questions for the end for the big integration discussion that we have. Okay, great. So our first speaker today then is Patrick McGovern, and he'll be speaking about Sinus Meridiani, landing site for human exploration, and Mesas Fluvial system.
All right, sounds like I can be heard. Okay, good. Does somebody hear some noise out there? Annoying buzzing sound. So this is a conceptual talk. This is based on the work of Justin Wilkinson, who's at the Johnson Space Center, who I've worked with on a project I'll talk about in a minute. He can't be here today. He has some previously scheduled travel to Africa. So he couldn't be here. He asked me to step in because I've worked with him on his concept. His concept is basically the large fluvial fan, which is something that's been only recently recognized on Earth, never mind on Mars. And I'm more of an end user of the concept rather than a originator or someone who's really facile in it. But we've been using the concept of a large sedimentary fan coming off, say, Tharsis in the early part of in the Noachian and Mars history to explain perhaps why the Olympus Mons volcano shows evidence for volcanic spreading and seems to be spreading on its base. And there's a number of structural and tectonic reasons why we think this is so. And Justin's concept of the megafan as a big sedimentary, wide sedimentary body that could provide that sort of basal detachment for Olympus Mons to do what it does. That's how I've been drawn into this sort of project, having some familiarity with the concept. We've also brought in Heath Mills from UH Clear Lake as for astrobiological input. But here's the site. Exploration zone map in Meridiani, which includes the opportunity traverse path in that area there. But there's a number of different interesting sites for both science and resource extraction that we can look at within this overall exploration zone. And we'll talk about each of them in turn. So the overall concept here, looking at the origin of the Meridiani sediment suite in this area here, as you look, there's a boundary defining a part where you get numerous valley networks up in the uplands to the south of this area, and they abruptly terminate at that boundary, and instead you have what's likely sediment deposition from materials that were transported in those valley networks in a different mode of transport and sediment production there. The idea that you have fluvial processes going on in this area is what's driving this presentation. So in a large fluvial fan concept, what you have is these potential stream base profiles covering up sloping sediment bodies that surround and engulf the craters and smooth out the terrain there. And this may be an analog, this is a diagram taken from a terrestrial setting, but maybe an analog for Sinus Meridiani. The large fan sediment bodies explain the layer structure, the low slope oriented away from the highlands, and lateral large extent as with nested large fans. So here's a really good terrestrial analog here with the Himalayas here and these big fans feeding rivers that ultimately flow down that direction. Kosi River and a couple of other ones where you have streams coming out of there and then forming these large sediment bodies. So what Justin describes as the Kosi River avulsions. Here you have basically a sequence of river channels that have been gone from 1736 to 1949. They sweep across the sediment body and presumably at some point will start sweeping back and create a sediment, a large sedimented fan. This is going to show the blue rivers sweeping across. Sorry about that glitch there. But you know, from here to there, you're just sweeping and producing a large sediment body. Now, where might we think about looking on Earth as a Mars analog? When I talk about Africa being a Mars-like continent, it's in the context of the one-plate planet scenario, where you have on Mars, where you have basically a uniform lithospheric plate. There's no plate tectonics. There's no motion of the surface with respect to the underlying mantle and whatever hotspots or plumes or whatever thermal anomalies might be going on there. And the continent of Africa, is moving quite slowly with respect to the underlying mantle, so it's a good analog for these one-plate planet type scenarios. And Justin has mapped a bunch of these potential megafan, a bunch of these potential megafans in various basins in Africa, in various locations. At some point, I judged that it wasn't necessary to go into all the details here, but just to get an idea that on a Mars-like continent on Earth, you might have a lot of these potential sediment bodies. Again, it's something that's only recently been understood, even in the terrestrial setting. So, overall, these things are a new class of landform feature on the planet. They're not just the freak endpoint in the alluvial fan continuum, but there's something unique and powerful about knowing about them and about what the sort of things they can do. And they are the norm in all the continental basins that are filling. So it's at the middling scale here, where you get a table of megafans in terms of a scheme of fluvial sedimentary bodies, where you go up in scale here and time scale. And the new stuff here we're filling in this box here, the megafan, or the sediment-nested megafans that goes between just a typical alluvial fan type system and a larger basin fill complex. So it's in the middle there. So prediction, we can predict where these things are on Earth now, or where they should be found. Megafans on Mars, this may not be the best example. Justin wanted to include it here because it is a striking fan coming off of Apollinaris Patera, and I was quite gratified to see that there are a few groups that will be looking down in here to get some advantage of looking at a rover landing between a rover landing site and a large volcano. That's pretty cool. We'll be seeing more about that later. But let's go back to Earth for a second, tweak the analog a little bit. Thinking about a common eroded upland lowland margin landscape sequence, where you get these, we were looking at the sort of layers coming in the original plot I showed, but when you get some erosion there, you might be exposing some of these things in the edge here, like you see over here in the Rocky Mountains. You've got upland sediment source, an eroded trench, and then the upland-derived sediments filling that trench. And you may be seeing things like that in our science region of interest 1, looking at there's some CTX imagery, stratigraphic relationships between the units of science Meridiani sediment street, especially the hematite pH unit margin, the value networks, and there's potential for habitability in the hematite pH unit. There's something that you have potential possible lake sediments with potential for habitability as well. Stratigraphic relationships, we're looking at the potential exposures of that sediment stack according to that analog we're looking at. Maybe some of these things get eroded off and then you see them exposed in this area here. 1B, the same sort of thing is going on here. You have the hematite pH unit potential for habitability, Meridiani suite, and underlying the MCT, Mantle Crater Terrain, with a bunch of current imagery available. Burns formation in hematite. Hematite is a big deal. Here in this area, you have field access to sites along Opportunity's traverse path. We can extend perspectives from Opportunity's operation and extend that over here. So science region of interest 3, Miyamoto Crater, stratigraphic relationships where the following formations meet: the Meridiani suite to the east, and the intercrater derived sediments to the west, where there might be things of interest there. And Miyamoto, of course, has this famous inverted channel. Access to the idea is that you have you carry stuff that may be more resistant to erosion and put it in the stream bed, and then when things erode around it, you end up getting a raised channel there. And it appears to be a precise analog for the widespread intercrater ridge terrain of the Meridiani units to the northeast. And the chrism response is evidence for phyllosilicates plus water plus hematite upslope, ideal terrestrial conditions for microbial activity. Miyamoto Crater, here's the chrism and the 3D DEM of that ridge. Might be some ideal conditions for microbial activity there. So let's think about what the large fluvial fan hypothesis does for us in terms of requirements for understanding Meridiani units as laid out by Hynek and Phillips. You can see that the large fluvial fan hypothesis pretty much satisfies, it pretty much deals with all the different aspects of this: the coherent deposition over the 100-kilometer scale, the exposures of these units over widespread, generally planar strata, developed conformally to the likely pre-existing shallow regional slope, formation towards the end of Noachian and continuing into the Hesperian, geographical association with both older and younger valley networks, significant compositional differences between layers, and it also deals with number 7, which is it shows that number 7 is really a non sequitur. The lack of evidence that the deposition took place in closed basins, as Justin's work shows, you don't need closed basins. Four, good. You don't. It's really non sequitur. You don't. That is not a requirement to explain things. So pretty much, large fluvial fan hypothesis has dealt with all of the things here laid out by Hynek and Phillips for that area. In terms of the science rubric, we filled out some of the matrices here. I don't think we necessarily felt qualified to deal with the atmospheric part there, but I wanted to make one comment about the potential for present habitability refugia. I'm kind of skeptical of really anybody putting anything green in that area here. I have my my understanding of the way microbiology works. There have been microbiologists have talked about how hyperthermophiles are at the root of the tree of life. The sort of thing that the life may have evolved first in that way. And if you're thinking that way, you're probably trying to keep a source of heat and energy for these critters as long as physically possible. So this line is talking about, is this where we're going to find, critters living today on Mars? I'm skeptical that any of the areas that we're allowed to look at engineering-wise, that is without the dust, is really going to have something like that, because the areas where the thermal and tectonic stuff is going on Mars, namely Tharsis, with by far the youngest examples of those things is locked out to us. So I'm really kind of, that may be a good thing in terms of protecting the planet from us and our biome. If you're thinking from a planetary protection aspect, it's probably, I'm thinking a lot of the areas we're looking at, they tend towards the Hesperian and when things were really going on. And the problem, the thing I have trouble running my brain around is like, what are these things going to eat for 3 billion years? You got to eat. So I'm kind of skeptical if anybody puts a green circle in there. But let's talk about resources. Hematite is, iron ore. I mean, it doesn't get any simpler than that. It's widespread and serviceability and friable host rock. So you have a potential to look at, the layered terrain with the hematite-bearing plains here and phyllosilicate-bearing materials in there. And that's the sort of thing you could get, extract resources from that sort of material. Possible water resource, this is something we need to look at in more depth. In the lowest areas of the Miyamoto and the trench between the South Highlands and Meridiani sediments, identifies possible lake basins by Newsom et al. May contain near-surface water. And this region map overlaps with the hematite unit. So it's some place where there may be water down below. And I'm going to skip over this. I'm not sure we've necessarily done the best job of filling out this rubric here. But again, this is more of a conceptual talk. So hopefully it'll set the stage for more discussion of Meridiani to come in the next talks. What we might want for data sets, we might want to widen the existing CRISM data set and targeted mode within the proposed exploration zone, and gamma ray spectrometer or maybe neutron detection instrument, like the friend instrument on the trace gas orbiter to come for characterization of the water signatures in the proposed EZ, more complete coverage at the greatest possible resolution to explore the correlations between the neutron signatures and the geologic features. And I'll end it there. Thank you.
Clark, Wilson, and Smith on first landing, southern edge of Meridiani Planum, and our speaker is Heather Smith. Great.
And how's it is loud? Okay. Okay, is this volume better? Okay, great. All right, so here is our, let me just use this, sorry. So our landing site is in Meridiani. Am I still on the microphone? Okay, great, thanks. So it's in the southern edge, and our landing site is right here where this little green dot is. Okay, so we have approximately 20 region of interest areas, and this is a good summary of it. We have Hesperian Evaportites, icy ramparts, Noachian Bedrock, Fluvial and inverted channels, the coastal sediments, and the reoccurring slope linea. I'll explain the science area and then followed by the resources. So first of all, we have the two formations. We have the Hesperian up here and the Noachian down here, and then we have this crater here, Bopaloo, that has possible ice ramparts in it, clay minerals, channel systems. This is a general just geology overview of our area. And the red circle, by the way, is a 150-kilometer area. Okay, one of the good things about this area is that it's also an area of low dust. So there is, well, both of them have low dust. One is dark, fine sand, which is this blue area, and the green one is fine, coarse sand. So it's just a good site because there's low dust. And in addition to that, for the landing site itself, this is a black square right here. And we have fairly flat, low dust again. There's very few boulders. And in particular, there's this hard stand that you can land on. And these are like centimeter scale thing, so you could like walk across this. It's not like it's a big divot. So it's fairly flat. Okay, so going on to the first science, so Hesperian Evaporites. So in these three areas, 1, 3, and 2, you have Hesperian Evaporites, and we can evaluate some astrobiology potential for past life biomarkers. We also have the atmospheric gases and impact glasses and the sedimentology of the area. In addition, since the Mir rover opportunity is there, we can also do some material science studies on the actual rover itself, as far as changes in material, et cetera, from being on the surface. And similar to what Ranger did on the lunar surface, is there any microbes growing inside the boxes or spores or anything that have still managed to survive on Mars within the rover itself? All right, and then this yellow eclipse here is the Schiaparelli landing eclipse for the ExoMars. Okay, our next main area are the ice ramparts. There's 3 main areas, 4, 5, and 6, and this is 5 right here in Lasso, and you can see the difference in the topography, like you can see from here to here, and these would be subsurface ice ramparts, and here are some references, so we believe these could be true. I know there's been a lot of discussion about ice today, but we think that there could be ice there. All right, and again with the ice, you have the present life. So in the spore form, it could be dormant, or it could be cells, or it could just be dead body parts that are preserved by the ice. Or you could also have the dead organisms, or just in general extinct life instead of extant life. So you could have extinct or extant life in the ice. And you also have isotopes you can look at, and you can do the preservation of the gases and the glass and impact glass, etc. And then for geoscience, there's a lot of different ages that you can look at. And then you have the Noachian crust, the sediments, magmatism, metamorphism. Anyway, it's just a really good site, of course, with the ice. Okay. The next one is the Noachian. Wow. Okay. Is that a little bit better? Is the Noachian bedrock. So here we actually have 2 slides that present this. We just couldn't fit it all in one when we go to the resources here. So the Noachian bedrock, first of all, the Opportunity rover is in site number 8. And we have the atmospheric gases. You could have the impact glasses. You have the Noachian, Hesperian, magnetism. And you could also, of course, pick up the rover for do the planetary protection stuff. And there are some hydrothermal veins. So this has got quite a bit of science to be done in it on the Noachian bedrock, and within a relatively somewhat small area traverse. Okay, and then you have the coastal sediments. So again, past life for microfossils, preservation of glasses, and the sedimentology of the Hesperian coastal environments. So then we have some where we can look at the Fluvial geomorphology and the actual sedimentology layering. So we could do some paleohydrology studies on it. There could be some microfossils in the channels, and you could also determine somewhat of the evolution of the Martian crust by studying the 3 different boundaries, the Noachian, the Hesperian, and the Amazonian sediments. But we don't know if there's any Amazonian ones there, but we know about the Noachian and the Hesperian ones. So there's fluvial channels and inverted channels both there to study the geomorphology. All right, and then number 20, this is somewhat new. We believe there's reoccurring slope linea, and this was provided by David Stillman. And you can see in these images, okay, there we go. You can see right here where it changes from here to here. You can just see a little bit of the coloration and change. And so that's what we think is the RSL areas right on here. Now this is a little bit steeper slope, and so you wouldn't be able to really, I guess you could walk up there or drive up there. I mean, anyway, it's a bit of a steep slope to be able to get to those areas. So it might be better studied by I like the idea of sending a drone there or something like that to collect samples. But there is possibly RSLs in this area. And of course, that could be the extent or extant life. the volatile gases, and then the salts, of course, because it's brines. So, and this is Site 20, so it's right outside the 150 kilometers, but it's very, very close to the eclipse. I mean, it's close enough. All right, now we're going to go to the resources. So that was the main science, and each of these areas offer resources. It would have to be a trade-off between whether or not you'd study it scientifically or for resources, because I think if you were to do it, start collecting the resources, then the environment would be less pristine, or wouldn't be pristine, and so it might, you might lose some of the scientific integrity of the site. All right, so we have the polyhydrosulfates, which have been discussed several times today at sites 1, 2, and 3. There's dark basalts, there's hematite, and then the magnesium sulfates. These could be used for water extraction and for metals as well. Yeah. All right, the second ones are groups 4, 5, and 6, the ice ramparts, and those, of course, could be used to extract water ice. Yeah, so that's that one. Okay, the other resources are 7, 8, 9, and 10, and that can be used to extract metals and clays. There's been hydrothermal deposits there, copper, lead, zinc, gold, arsenic, and silver. And there's also gypsum, and there could be some like newer basalt in some of the locations. So that's metals and clays in that spot. Okay, and then again we have metals here. Not as many clays in this area, but definitely still metals. And you have the hydrothermal deposits as well. Oh, sorry, there is some clay alteration here. And then construction material is this other group, 11, 12, and 13. And this is basically just the sand, the gravel, and the gypsum, and we have hematite as well. So it's a good engineering area for building. We would consider construction material. Okay, and then the RSL, water and brine, can be used again for salt deposits, regolith material. I'm not sure, other than water, for both science and for drinking, I'm not sure exactly what the brine would be used for salts. Didn't know what we would use salts for. Okay, and then here's just the general. We read this easy sum as a summary as opposed to sum them. So in it, 17 of our sites have are yes to the potential for past habitability life. Anyway, here's a sum of it. In parentheses meant that it was partial support, but we have most of the things covered scientifically. Actually, we have everything covered. Research-wise, we don't really know about located less than 3 kilometers from their processing equipment site, since there's none there. So yeah, so we have just about all of the resources covered as well, except for the well, it's not located in the northern hemisphere. Okay, I think I'm actually almost done. Yeah, I'm done. So what we do need from here is more high-rise images for the regions of interest, and to look for and confirm the reoccurring slope lineas in the craters, and then checking for the ice as far as the depth of the ice, et cetera, in the Basaltic craters and the South Crater with Sherrod. And then also determining the trafficability better with the best routes that you could traverse, for example, because we know the area is trafficable, but we haven't taken analysis as far as the best routes to go and the time that it takes to go there. So yeah, that's it. Great. Okay, thank you. Just going back to the first slide. Yeah, thanks. Yeah, and then, oh, here's the headset. Good luck.
Thanks very much. Thank you. We gained a little time on that. Thank you. We'll save it for the integrated discussion we have. We have 2 more talks. We have the Land of Opportunity, cute, Human Return to Meridiani Planum, Barbara Cullen and Mike Siebert, and Mike's going to give the talk.
All right, so hopefully the microphone's on. Sounds like it is. To begin with, I am not a geologist. I'm not a planetary scientist. I'm an engineer. So if I screw up any of the science, and that goes for Barbara who's watching, I apologize in advance. I'm Mike Siebert. I am a rover driver and the lead flight engineer for Opportunity, so obviously I'm pitching a return to Meridiani Planum. So why do we want to go back to Meridiani? If we look at it, the big thing is safety. That's what started this whole discussion between me and Barbara, is it's low, it's flat, it's stable. The top cover material is over this lighter bedrock material. There's effectively no rock abundance. This is almost a 270-degree field of view image. The curved horizon is an artifact of the image pointing and the processing when we were working some engineering issues on the vehicle. But it is flat as a pancake for the majority of Meridiani, which might be boring to look at, but it makes it incredibly safe. It also reduces the wear and tear on mechanical systems. The Opportunity rover was designed to go 1 kilometer. We only expected 600 meters out of it, and we've gone more than a marathon. So we're at 42.5 kilometers right now for that vehicle. So it's amazingly benign on wear and tear. More with safety, we've got really good solar insulation. We are equatorial. There's one of the things you'll see in the rubric saying, are you northern latitude? We are close enough to the equator that for the purposes of this, we are northern latitude. We have a more benign thermal environment because of where we're at. We have good lighting. Glare and glint are not just a problem for astronauts that might be driving a rover around. They're problems for those of us operating robotic vehicles. If we have glare from the sun being in our cameras, we can't have our terrain images processed correctly, and we're not able to drive as far. That's all. It's a known dust environment. We've been measuring the atmospheric opacity almost every single sol for coming up on 12 years. We can tell you that for more than a quarter of the Martian year, it is incredibly stable and predictable and just follows the current trends. We also know that dust is deposited and removed from the surface at different times of year. This is Opportunity at the beginning of the previous Martian winter and then a few months later when it was cleaned free. And we do see this consistently Mars year to Mars year. So planetary protection, there was a lot of discussion about this yesterday, everything ranging from we don't need planetary protection if we're sending humans because we're going to contaminate the surface, to we can't send humans because we'll contaminate the surface. Well, look at it this way. We've already landed there, and while our planetary protection standards are strict and based on Viking, that's not a non-zero contamination. So we have already effectively contaminated part of the Meridiani site. So forward contamination has likely already occurred, although small, by dropping things like the heat shield and the rovers and everything all over Meridiani. Backwards contamination, it's a very dry and barren. We haven't seen habitats for extant life that we've been driving over, so that's going to minimize our potential for backwards contamination. And we've also characterized for more of a non-biologic contamination for the crew, surface materials using our in situ instruments. Another reason to go there, follow-up science. We could do follow-up science with a surface proving ground mission. That was very briefly mentioned yesterday during the Evolvable Mars campaign presentation of doing some initial scouting. You're not going to have this huge base when the first crew shows up, so what are you going to do? We can do some immediate follow-up science going after our existing targets like this Pinnacle Island rock, which was exposed when Opportunity broke it free during driving, and getting extra context for our existing measurements. We have one rover with the fixed cameras on the vehicle, so we've always have our perspective for looking at all of these different observations. But a human, we can walk around. We can see in real time the effects of the lighting angle. We can, over the period of the couple sols, we can see this in real time. With a rover, we're limited to the images we take and when we take them. For long-term follow-up science, we can go back and we can follow up on the measurements we've already taken. We can get better context. And we can continue similar measurements after Opportunity's mission ends. The asterisk there is, yes, I know we're talking about the mid-2030s here. Don't bet against the rover. It's a good way to lose money. Opportunity might still be running. It's an outside chance, but it's a 3-month mission coming up on 12 years. So this slide has been shown before. This is Sandra Wiseman and Ray Arvidsson at WashU put it together, showing the general geologic outlay of Meridiani. The red area is the nice flat surface that we've been driving over for most of the time. The traverse map, this is old. We are now down where these clay minerals are in Marathon Valley. But to lay out your exploration zone, I overlaid this on some of the daytime infrared imagery that was available in Google Earth to show where we're looking at. So for the field station, it was actually difficult to think of where do you actually want to put this field station? What do you want to be able to reach? and how far away are your resources. You can park it right next to your resource, but if you're up here in the crater terrain, you'll have a more difficult time landing. But anywhere that's in this red region would be a nice, safe landing site. Also called out would be a surface proving ground mission landing site, and that dashed line is a 20-kilometer walk-back radius. That's for an unpressurized rover support. So we do have some regions of interest. They are circles. They may expand farther. The larger one, resource region of interest 2, is effectively the entire red Meridiani Plains area. So for our rubrics, we have filled these out as best we can, and since these are all going to be collated into one big one, I'm not going to spend much time on it. Barbara took care of all the science rubrics because, again, engineer, not a scientist. And then also we've got our resource ROIs, but hopefully these individual slides for these will make it a little bit more clear. So for science, again, apologies if I screw any of this up. So we start off with the Meridiani Plains. It's regionally extensive and contiguous units that have datable materials. We've got potassium-rich sulfates all through it. We also have sedimentary sulfate-rich deposits, such as here on Burns Cliff, with gypsum veins and hematite concretions, which are known as blueberries due to how they appeared in our false color imagery. For region of interest 2, this is the rim of Endeavour Crater, which includes where Opportunity is currently exploring. So we've got phyllosilicates and sulfates detected. We've seen the phyllosilicate spectral signatures, which correlate with the polygonally fractured bedrock in high rise, which you can actually see on the surface, and are in place for their stratigraphic context. We also have some groundwater mineral interactions as seen in these gypsum veins. This image was taken about up here that show that there was a previous wet environment on Mars. So for regions of interest 3 and 4, I do have a map at the end so we can remind everyone where these are. These are down in what is known as the channel system. These are channels that go from the higher ancient crater terrain down onto the plains. And it appears that there are phyllosilicates in the walls of these areas, including craters, and they are preserved with the overlying material. The chrism phyllosilicate spectral signatures, again, correlate with the polygonally fractured bedrock and high rise, and we have stratigraphic context for it. Continuing on, 3 and 4 are very similar due to where they're located in the boundary between the plains, the crater terrain, and the channels. So we've got intact Noachian Hesperian contacts with the datable phyllosilicates in there, and we may have unaltered basalt. And then we've got an identifiable contact between the plains and crater terrains, and as Barbara calls out here, conveniently cut by a channel for access. Moving on to the resource ROIs, which is more of where I took over. So this is ROI 1. This is down in that channel system area. It's a water resource. We do have phyllosilicate signatures. And I took a look at the route up the channels with the existing high-rise and CTX coverage. I put on my rover driver hat and actually said, can we get there? Because we are going to be climbing up an elevation. We are going into a new terrain unit that we haven't driven on before. And based on the high-rise and CTX imagery, it does appear that there are channels that would allow us to take a rover and easily go from the plains where it's nice and safe to land and you can have your base and work your way up into this crater terrain. Resource region of interest 2, this is much more expansive because this is a lot of the surface covering. We have extensive imagery. For food production, there was talk about wanting the basaltic soils. Well, we have that all over. For metal and silicon, we have the hematite blueberries. And we can get to this with automated systems because it's right on the surface. There have been discussions on systems from everything that could scoop up the surface coverings to vacuums being proposed. Getting it off the surface is easy. It's loose. It's right there. The high-rise image of north of Victoria Crater shows you can see the bedrock intermixed with this surface covering. So for region of interest 3, these are the hydrated clays. We are currently here with Opportunity. The Marathon Valley arrow, that points to about where Opportunity is right now. So we are actually exploring this region of interest actively. You can see the images. This is false color of down in the valley. There is a strong phyllosilicate signature thanks to chrism observations that have been done. This is what drew us here. We're getting the context for that right now with the rovers. But we do have a proven traversable route into Marathon Valley. It's been done. That is not anything that we need to actually discuss whether or not we could get in there. Slopes are good. We can get through. Again, we are actively exploring this. These images came down at 11 p.m. Central last night. So this is how fresh our data is. So region of interest 4, this is way out on the edge of the exploration zone from where I put the field station. This is west of Bapalu. Again, it's got basic surface covering. There was a phyllosilicate detection from Chrism there, but it's very limited imagery from what I was able to find. It would take a lot of traversing to go there. You can't drive straight through the Bapalu crater, so you'd have to go out and around. And finally, region of interest 5, this is right under where I put the field station. Food production, one thing, low latitude, no shadowing features. It's Meridiani. I showed you that panorama where it was flat as a pancake. There is nothing to shadow a power collection facility. Probable surface covering is those basaltic sands with the hematite spherules, which gives us right there, we can pull the metals out and get to it autonomously. Also, with this being this flat, one of the other options is, since autonomous systems will have to assemble any future base that's being put together, we're not going to be sending all of the hardware with a crew due to the landing constraints. In the event we wanted to move the field station, the autonomous resources with this nice flat terrain, excellent power, we could relocate as components of the field station or the entire field station itself to another region in Meridiani to get closer to resources if needed, get closer to science if needed, and allow us to maximize return crews to the same exploration zone, but actually do it at different locations. It's a balance between a sortie mission and a return to the same base mission. So for our data needs, going through, this is the high-rise coverage. All the red dots shows us what we have. The landing site was put in some high-rise imagery that was being done for a possible MSL landing. CTX coverage is pretty expansive because we do have a rover here. And Chrism, it's a little harder to see in the projection, but this is down where our resources were, which will lead towards that. And we do have the extensive coverage over Victorian Endeavour craters. So what do we need for science? We want to expand our Chrism coverage over the science region of interest 3 and region of interest 4 areas. And for resources, it's approximately the same area. The Chrism oversampling that was done to draw the Opportunity rover to Marathon Valley for science, we can use to figure out what the extent of the phyllosilicates are there as a potential water resource. So to end, I just want to put the map back up because I know everybody's filling out their little scorecards and review cards, and it was always a little difficult to do without being able to see where everything is. So this is our proposed exploration zone for returning to where Meridiani is. Where Opportunity will be when humans get there, I don't know, but it will likely still be within this 100-kilometer radius from the field station. And that's all I've got.
Head of Opportunity going, yeah, when everybody in there watching, they go, good way to go. Thank you. So this is the fourth and last talk in this equatorial session. We're moving to Gustav Crater, and the presentation will be given by the author, Alex Longo. And the talk is a landing site for human missions to Mars in Gustav Crater.
Good morning. I'm Alex. I'm a member of the Mars generation, and it's my dream to walk on Mars. So I'm going to continue this series of talks of Go Where You Know with Opportunity's twin, Spirit, and Columbia Base in Gustav Crater, which I think is a really compelling exploration zone. And I would like to thank my co-authors, Jim Rice and Steve Ruff, because they've taught me a lot of what I know about this EZ, and have helped me out a lot becoming a planetary scientist. Why should we go to Mars in the first place? Well, Robert Goddard was one of the visionaries who first envisioned traveling to another world, and he said that it is difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. When he challenged people to go to the moon, President Kennedy said that we choose to go to the moon not because it's easy, but because it's hard. And that really holds true today. Mars is the next hard goal for human spaceflight, and traveling there will produce huge benefits for all humankind. This is the Gusev Crater exploration zone. It's a little bit hard to see, but there's the rim of the crater here. It pretty much covers the whole EZ. And the surface field station is in the center. We have 8 science ROIs and 2 resource ROIs. 1 resource ROI is nearby, the other's a little bit farther away. In terms of engineering, this is a very safe site. Don't worry, nobody's going to die on landing. There are very few, if any, large obstructions, and any that are easily avoidable by a human pilot. The surface field station is also adjacent to 2 science ROIs and 1 resource ROI. So you can pretty much just step out of your lander and start doing stuff. And the whole crater is very flat, so it's really easy to get to the really interesting sites as well. And just for some context, Spirit landed around the same area that the surface field station will be in. Here's the rubric. Wait, where's the disclaimer? Anyway, this rubric was filled out by an amateur planetary scientist. It is not intended to be a source of fact, but simply rather a source to influence further discussion. So please feel free to comment and change some stuff on this. Same thing with the resource rubric, just some potential resources that we could use. The first science ROI is the Columbia Hills. That's the roving ground of Spirit, and it's been imaged to death by HiRISE because we have a rover in that location. And it's only about 3 by 5 kilometers, this area, but there's this huge grab bag of geological samples that you can just collect, from evidence of an hydrothermal system to carbonate, clay, and sulfate minerals that are indicative of ancient lakes, periods of intermixed volcanic activity and activity by water, and even some interactions of the surface with water only 2 to 5 million years ago, which is like yesterday in geologic terms. And we've also got, to top it all off, a datable Hesperian volcanic surface. And we also have ground truth. The astronauts will know what to expect. It's safe, they'll know the hazards, and they'll know what are the best places to do science. This is just a visual. We're using some Spirit images, and also one image from HiRISE of the ROI-1 and some of the interesting rocks that we hope to take a look at there. And we also have an analog environment for this hydrothermal system as well. Steve Ruff, who was my co-author on this paper, has been doing some work with El Tatio, a hydrothermal field in Chile, and comparing it to the hydrothermal field that we see in the Columbia Hills. And the rocks are practically identical. The structures in those rocks are practically identical. And even more importantly, El Tatio is teeming with microbial life. And some of the structures in the rocks at El Tatio could potentially have been produced by life. So in the Columbia Hills, we not only have a habitable environment, but a potential biosignature, which makes this really interesting. So stay tuned for more results on that analog there. ROI2 is the Mesa. It's a group of big mesas located at the mouth of Meridiani and Vallis. We don't really know their origin because we don't have much coverage. They could be a flood deposit, they could be a delta remnant, or they actually look a lot like chaos terrain. And these things are just really cool. They're 400 to 500 meters tall. And imagine the view you get from the top. That's what it would look like if you were an astronaut standing on top of one of these mesas. And they're also surrounded by these volcanic plains that we can get absolute age from. ROI3 is the Eroded Rim of Gusev Crater. And this poor crater rim has bear witness to lots of activity by water, lava, and wind. That's why it's really degraded. Extensive alteration by water, and it's a record of climate change over 4 billion years of the history of this planet. ROI4 is on the other side of the crater rim, and it's a bunch of secondary impacts, which pretty much punch holes into the windows of the past of this area. and the stratigraphy in those walls of the craters could reveal something about the history of the region. And then note this smaller crater in the middle of the larger one. You can just see these blocks of terrain on the bottom. I don't know what they are. And then a really fresh rim. So that crater was probably formed pretty recently. ROI 5 is Mars Vallis, which is a 600 kilometer long meandering river channel that flows right through the rim of Gusev Crater. And obviously it's the postulated source of all of the water that once filled this basin and the minerals that we saw there with Spirit. And the layered rocks in the wall can also preserve past habitability and evidence of what the environment used to be like. ROI 6 is a bunch of clays. That ROI, I'd say, is about 15 kilometers long, so very widespread. And they're both iron-rich clays and aluminum-rich clays, which indicate climate change in the presence of water, and lots of water at that. Based on data from other sites, from Curiosity and Opportunity, we can tell that this environment probably was habitable. There was a neutral pH. And bonus, these are hydrated minerals. We can even use them as a resource if you want. ROI 7 is Etched Terrain, which is just a really cool feature. We don't really see anything like it on Earth, so it definitely has a lot of applications to understanding Mars and the processes that are going on. But you can see that these little mesas of etched terrain sort of all are oriented in the same direction, and they could have been formed by glaciers, or they could have been formed by erosion by wind. And they have a similar thermal inertia to ancient rock layers like we'd see with clay minerals. ROI 8 is the Basaltic Plains of Gusev Crater. It looks boring at first, but actually it allows us to interpret absolute age, which can then calibrate our crater counting. So it's actually pretty important. And as a bonus, in this ROI, we've got this tectonic feature, a wrinkle ridge, sort of slicing through the middle of it, which is from the time period when Mars's crust started contracting. As for resources, look at Gusev right here. This is the same gamma ray spectrometer map from Mars Odyssey. But it really is pretty much the only equatorial site with lots of water. Greater than 2% water abundance at least. Actually, judging it's more between 7 and 10% from gamma ray spectrometer. It's almost like a polar site in terms of how much water we've got under the surface. And RI1 is another group of etched terrain located right next to the landing site for easy access to resources. And none of the resource ROIs I'm discussing in this presentation would jeopardize planetary protection concerns as much as some of the other ones we might be considering. Resource ROI 2 is a group of Pingos. What's a Pingo, you may ask? It's really just a fun way to say a mound of permafrost. And permafrost is an extremely effective preserver of organic material and even fossil microbes. Once some scientists dug up some permafrost from a couple thousand years ago, heated it up in their lab, and some microbes that had been hibernating woke up and started swimming around. And you say you want 100 metric tons of water? Well, we've got about 20 by 20 kilometers of the Pingos. There's your 100 metric tons of water. And the only drawback is that they are about 30 kilometers from your easy center, so you would need to do a bit of driving to get to them. Resource ROI 3, the Great Spirit Rescue Mission. It's not really technically a resource ROI, but if you're an astronaut who's going to be on Mars for a year or two, it's pretty important. It's an enrichment resource. The astronauts in their free time, if they're looking for something to do, they can fix up Spirit and repair it as a tool for future explorers. Here's the astronaut from The Martian doing the same thing with Pathfinder lander here. In the words of Mark Raymond and the Dawn team, if it isn't impossible, it isn't worth doing. And Jim Rice, who's my co-author in this presentation, has told me that Spirit, looking at Spirit can also inform us on how mechanical components of our landers weather in the environment. So we can tell how our surface field station and all the equipment we have is going to stand the test of time and how often we're going to have to replace stuff. Important if you're going to be risking human lives sending people to Mars. As for data needs, our number one priority is a return to this region with the Mars 2020 rover. And this is perfect for Mars 2020 mission objectives, like I mentioned with that grab bag of samples. And I can discuss that in more detail if you would like. But those are all just from Science ROI 1. And it's honestly in a 3 by 5 kilometer area. It's just about the best mineralogic diversity you could possibly hope for. And it would also photograph Spirit, acquire that environmental data. Better that you have that before you send humans than after. And then it would confirm or disprove that potential biosignature in the hydrothermal system. If it confirms it, then interest in sending humans there would obviously be very high. And finally, we would ground truth at least one science and at least one resource ROI. We're looking at 3 to 4 ROIs total over what hopefully will be a 10 to 15 year mission for Mars 2020. Priority 2, just a little bit more in the near term, is CRISM and high-rise coverage of all the ROIs except for the Columbia Hills. And what we're really looking at is those mesas. What are they, and how do they play into the story of Gusev Crater? So we definitely want CRISM information on that. And then priority 3 is some data with that Marsis radar instrument on those Pingos. Are they really permafrost mounds, or are they something else entirely? Could they be a resource for astronauts? We really want to know that so that when we send astronauts, they'll have the correct resources to survive on the planet. Here are the 7 men and women that we will be naming Columbia Base after. And I would just like to say that in honor of the past, we are innovating in the present and hoping for the future. And it's our duty to explore space for future generations, for ourselves, and for the entirety of all humankind. And that's why we are exploring and why we're going to another planet. In conclusion, I'd like to quote Steve Squires, who led the Spirit rover mission. He said, "What I really want for our rovers, more than anything else, is boot prints in our wheel tracks." And what a better way to honor that statement than sending humans to the Spirit rover landing site. Thank you. I'll just stay up here to take questions for the discussion.
Can we get all the presenters down here too, like we did the last time? And I really want to thank everybody. Is this on? Is this on? Yeah, great, thank you. So I want to thank Pat, Heather, Mike, and Alex too for the great presentation. Actually, all the presentations are amazing. There's like nuggets of ideas and all these things that are really cool. And our job here is to try to synthesize and start extracting these things in a way that'll support where we're trying to go. And it's fun to have Alex as a member of the Mars generation. So it's cool that he's here. I guess how old will you be in 35?
I'll be 35.
Oh, perfect. Okay. Alrighty. So since I get to run the session, I get to ask the first question, and I'm actually going to ask Alex to talk a little bit about his ideas. I'm going to get my little note about the Pingos and your belief on those in terms of a potential water source and what the data is that would lead you to believe that actually might be a significant water source. Can you talk to that a little bit?
Well, my belief on the Pingos is that they are permafrost mounds. They look an awful lot like ones we would see on Earth. And I think there's actually not one but 2 scientific papers available on that. That's how I got that idea. I believe they're by Natalie Cabral, I believe, was the author of those papers. And then, but if they really are a water source and we can prove that with Marsis, then they really would be a valuable resource. That's a whole wall of water in 20 by 20 kilometers of permafrost mounds. Okay. Does that answer your question?
It does, thanks. And I would like to, is there any members of the steering committee, if you have any immediate questions? Okay, now I'd like to open it up to everybody. If you fire away. So where do we have some? Yeah, up there. If we can get a mic up there, please. And again, guys, great. Thank you so much for all your work on this. And who wants to ask a question next? Because I want to make sure we get the mic. If we can get a mic up here too. Go ahead. Yeah.
Okay. Yeah, Jeff Plout from JPL. A couple of the presenters mentioned sounding.
Yeah. Can we help get that mic? Is that? Okay. Yeah. We'll repeat the question. Go ahead.
Regarding the Pingos, what's the diameter of these objects?
Okay.
Good question. I actually didn't check the scale. I'd estimate maybe, I don't know, they vary in size, maybe 50 to 100 meters long for each
The
Pingo.
problem with radar sounding from Marcus in particular as well is that the objects need to be on the order of
Bullshit again here, but let's get this fixed for you.
to get a reliable. So that's going to be
Okay. Well, the whole region is 20 by 20 kilometers, and they're pretty densely packed. So we can at least try. We might get some data.
Okay. And regarding the Rampart Crater blankets as a resource, I think that's a neat idea, and there are such deposits that seem to continue, but they're in the mid to high latitudes, as we've seen with Sherrod and Daniel Munis has written this up. So to expect those to be at low altitudes in the equatorial zone is, we haven't seen anything like that on Sherrod.
Can you guys move down here too? Just
Yeah, sure.
I think I might be blocking you. Yeah. That's great because we want to see you on Ustream too. Okay. Do we answer your answers? Yeah.
Okay, thank you, and letting me know of that. So, yeah.
Okay. Great. And then we have a question up here.
Hi, yeah, this is just kind of a general comment. I know that I think for Sinus Meridiani, that's you, right? Matt's shirt, yeah?
Yeah.
Okay. You had mentioned that like biological things need food and there's nothing there for them to eat. Just like a general statement for everybody who's considering mentioning things about astrobiology, there are like existing organisms on Earth that they're like chemolithotrophs that use chemical reactions in rock and things like that. So whatever you would typically consider as what things eat might not be the case on Mars. So you should kind of keep an open mind about that with your sites.
Yeah, that's fine. I'm not talking about critters eating, processed cheese from supermarkets or anything, but my my argument was that if you buy the idea that hyperthermophiles would be the most likely organism, and chemolithotrophs would come off of that, you still need a source of heat and energy, and
Right, so-
volcanoes provide that sort of
Right.
thing, chemical energy in terms of the materials coming up and the heat. Those resources are in areas that haven't been active, say, since the Hesperian, are definitely not, there's orders of magnitude less energy going into systems like that. So it's a matter of the ultimate source of the energy, chemical energy or thermal. It's most likely to be, to my mind, Tharsis rather than places where we can't look because of the engineering constraints, rather than pretty much everywhere where we're looking at this in this meeting.
Right.
Okay. Next question. Yeah, Matt. You're going to get. Yeah, I think we're getting your mic there, Matt. No, that's fine. Y'all keep the mic up there. Yeah, you need to have one.
Hi, this is a comment from Mike and the other Meridiani files. So you heard that landing on sediment could be problematic, but fortunately, as you well know, at Meridiani there are huge expanses of pretty much outcrop. So you might want to tailor your landing zones specifically to areas in high-rise images that have Burns Formation in them.
Yeah, and I did take a good look at that. It's with the ability to see the outcrop between some of the ripples, I definitely biased the landing sites and the habitat sites to have underlying outcrop under the shallow ripples.
Okay, other questions? Yeah, right here.
Just the discussion that we had about hyperthermophiles. Okay, that would be a nice organism to find. But what we learn, if you look at in the Atacama Desert, then actually the last organism to find in the desert region, which Mars is an extreme desert, is organisms that live in evaporites. So that use the liquescence, basically get the water directly out of the atmosphere. So that would be a nice model organism, and there are locations on Mars where this would be an option.
Any comments from you?
Well, I don't think we should be greedy. If we find life on Mars, it will be the greatest scientific discovery of all time. So I don't think right now we should be focusing on what type of life we should look for. Instead, we should go where we have the highest priority, where we have the highest chance of actually finding that type of life. Does anyone else have any other comments on that?
Anybody? Okay, next question. Right here.
Jake Bleacher, Goddard Space Flight Center. I think I have more of a statement to make now that we've listened to several talks about different spots where we have already put assets down and they've been exploring. I think you have all made compelling reasons to want to revisit some of those sites. One of the things I'm hearing is that we've collected a lot of data there, essentially recon data, both scientifically and technically how to move around. That point kind of argues to me that maybe we also need more recon rovers moving forward. And we talked yesterday in several of the early presentations about whether or not we'll have other missions supporting what's going on. And I think that's an important point. You've all demonstrated that having that data on the ground is important for moving forward with humans. But I want to make a broader point about the human exploration that we're talking about. We talked yesterday about humans revisiting these sites maybe 4 or 5 times, maybe more. That's going to be probably really expensive. And in my mind, we've talked about the idea of other SMD missions going along and complementing Mars exploration in general. But we also have to think about the reality that this endeavor might gobble up all of HEO's money and all of the Mars money in SMD. So there's a potential for, if we're talking about revisiting some sites where we've already been at, that we get into a situation where we found the needle, but we've completely removed the haystack. And so we've been asked to talk about what other observations would be important for going to these sites. And most of the talks I've seen have been talking about observations of the site. But I'd like to also remind folks to think about what observations planet-wide will help us understand the context of these sites within the overall history of Mars. So I just wanted to get that point out there. I didn't know if it was better to bring it up at the end, but it seemed like now, after a number of really good talks about why it's great to go to places where we already have data, there's also the caution about that becomes the only place that we've really visited for decades in a row as we move forward with human exploration.
So, if I might, so I think your point is essentially so another way of saying what I was trying to say. There are actually a lot of reasons why we are probably going to have to do precursor missions. Just not only ground truthing the site, but you're probably going to run ISRU equipment, set it up, the real production stuff, and run it, for 10 years at a time in a real Martian environment. That's just one example. So that's why I was kind of poking on this trade space, if you will, between things we know, and there is a logic for doing that, which is really the logic all these guys are building on. Vice, recognizing that if we do a larger search across the planet, and there are obviously very big voids of data, which is really what your point is, what I hear you say. So there's a balance that we have to try to find. But and I would welcome any thoughts you guys have.
Well, the thought that I've got is by advocating these known sites of Gusev, Gale, Meridiani, we are concerned, your concern's valid that we're going to chew up all of the Mars money. Forget just chewing up all of the Mars money. These precursor missions could chew up most of SMD if they wanted to. So if we're looking at trying to have a minimal impact on the rest of the robotic exploration program while focusing the humans on going to Mars, the most cost-effective way is use the data and the assets you already have. Use these as your stepping off point. Yes, it's the needle in ignoring the haystack, but if we don't want to forsake the rest of the solar system to put boots on the ground on Mars, we may need to start with that needle we have instead of what might be somewhere else in the haystack. Anyone else?
Any other comments? Okay, next question. Right here. Oh, hey, go ahead.
Well, also, I'd like to note that Spirit traveled only, I'd say, about 8 kilometers. Opportunity's gone 45. Those are pretty good distances, but we're talking about an exploration zone that's a circle, 200 kilometers in diameter. So what I'm seeing with Gusev and Gale and Meridiani, all of those sites, is that we have the ground truth, we know the site's interesting, we know it's safe, we know where we want to initially go, but that exploration zone also has tons of unexplored targets in it. So I think it really is almost a perfect balance, and we've got the ground truth. So that's one of the reasons we consider going to one of these sites.
Any other comments? Okay, over here, right here.
Okay, my question is, none of you kind of mentioned about affecting human missions following radiations, informations, and then pressure, atmospheric pressure, and then wind speed directions. So none of you mentioned about it. Any comments?
Well, we only have 2 weather stations that have been landed on Mars. We had one on Mars Phoenix, and we currently have the one on Curiosity. But the wind speeds at Meridiani were evaluated for being able to land the Mir landers. It ruled out Valles Marineris. So we do have some characterized wind speed. We do have direction. We do have images of clouds moving across the sky and dust devils moving across the surface. But for radiation, the low atmosphere, it's a little bit of a blocking. It's not that great. You're going to make a much better luck of shoveling all of that, the top cover material, the basaltic sands, into sandbags and throwing it on top of your habitat. I didn't have time to present a full "this is Mike's architecture," but there are definitely considerations for how we can preserve humans and take into account all those countermeasures we need at the surface. And I can talk to anybody at the break that wants to talk about it. I do have ideas for that, but that wasn't inside the scope.
Okay, and one other comment I would make for those who are on Ustream, we do have set up a temporary Gmail account to take questions online as well. So that we're going to start showing that up here so that we can have that as well. So next question, right here, Stan.
I've noticed a lot of questions talking about what more measurements we need, what kinds of measurements. I just want to suggest something that I think has been missing from those questions. There's a lot of talk of orbiters, and there's a lot of talk of rovers. How about something in between? If we could get a balloon or an aircraft or something like that. Right now, one of the most difficult things to do is to tie orbital scale observations to geologist scale observations, so from Google Earth to Google Street View. On your computer, when you make that transition and zoom in, you go through a lot of aerial photographs. So I'm wondering if the community might want to consider whether some mid-scale observations might be valuable to help us answer some of these questions.
That's a really cool idea. Yeah, over here. Can we get a mic over here?
Yeah, just to follow up on that, there is an idea right now of a balloon-borne neutron spectrometer for finding some water. So that's something that's definitely worth considering. And so I've got a print-only abstract for that.
Okay. And let's see, we'll go to Rob back here in the back, and we'll get you next. Okay. Thanks.
So I agree with that comment about the geological context, and having been on a geology field trip myself and hiked for 2 days to get a sample, which I wish I could have had in 10 minutes, I became a firm believer in aerial observation, and I'd like to point out that in situ resources can be used as propellants for unlimited travel on Mars. So don't forget that we can build hoppers on Mars and fuel them indefinitely by using in situ resources. And I think that's an excellent suggestion and one that's been overlooked, maybe for risk reasons, but for geological context, nothing beats a Google Earth or Google Mars view.
So, thank you, Rob. And I would say, as we get these kind of ideas, really think about saying them so that we can start building, because we are building a report as we go along here, so this is really key, so thank you. And then we got right here.
Yeah, I had another sort of asset-related question. You mentioned the possibility on future orbiters of having this type of neutron or gamma ray method. Could you elaborate a little more as to what the potential advantages or disadvantages of that type of method is versus the sort of near-infrared capability that you have with CRISM?
Do you guys want
Maybe in terms of like the different things you can do in terms of detecting water?
You're talking about, I think in my slide I mentioned. Yeah, that was input from my co-author, and I'm not really an expert on those methods. So, I mean, basically we wanted to characterize the water a little bit more. If there was, one of the important things in that rubric is for both the science and the resources, how much water is down there, and getting more orbital data on that, especially with new instruments like potentially the new neutron spectrometer on the upcoming Trace Gas Orbiter mission will be useful. I'm not really that's not my field, that's not my expertise.
So I'm going to skip, I'll get to you in one moment. Rich Zurich is actually on our next SAG, so that is actually looking at orbiter options. So let me let him talk, and then I'll come get you.
The difference between the thermal measurements and the neutron spectrometer type is the depth that you can get to. So typically we're at skin depth with looking at diurnal measurements, and a little deeper if you use seasonal measurements from temperature measurements at the surface. The neutron spectrometers and others go a meter or more. However, there's the issue of the spatial scale. And right now they're striving to get to sub 100 kilometer kind of scales. And there's some debate about that with the Lunar attempts to do that on LRO and such, about whether you really get such a collimated and focused part. That was the discussions that we've had in the next SAG.
Okay, great, thank you, Rich. And right with the red shirt, the one back here. Well, we got a few minutes, so we're good.
Hi, Laura Kerber, JPL. I just wanted to elaborate on what Rich was saying. Kind of, you have the visible near-infrared data that can, if you have water, say in a mineral or something like that, then we can tell kind of what structure it is and in what context it is. Whereas then with the neutron spectrometer, you can often tell, okay, there's excess hydrogen here, but I don't know in what form that excess hydrogen is. So then when it's near the poles, we maybe assume that it's in ice. And when it's closer to the equator, maybe we assume that it's in some sort of mineral structure. And then, what Rich was saying, that there's, a difference in depth. So if you look with near-infrared visible spectroscopy, you can see in, the first nanometers of the surface. And then if you're looking at thermal inertia, you can see tens of centimeters down. And with the thermal inertia, you can tell something about, modeling what is in the subsurface, but you also don't know. In that case, you're pretty sure that there's some kind of ice going on in there, maybe in the regolith as pore ice or as ice lenses or something like that. But it's harder to tell. There's a lot more things that go into that modeling, like grain sizes and how much grains are touching and stuff like that. So I think and then there's the radar, kind of on top of all of that, sees at a different depth and sees a different thing, the dielectric constant of what's going on in the subsurface. So I think the combination of all of these things will be really helpful, and it's tough for us to figure out, okay, this technique is excellent, but we don't have a good enough spatial resolution, or this technique is really good, but it's not in the right depth range, So I think a combination of all of these data sets is needed, and we need to really kind of look in and see in what case do we need like neutron spectrometer data that's really the most useful for our ISRU, but we need high resolution, blah, 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 blah.
Okay, and we got, did y'all have a comment you want to make to that? Okay, and then last question right here, as we're running out of time, and we got someone tying in from the Ukraine on the next one, so we have to get all the interpretations.
I'll keep it quick. It's just more of a comment. I think it's the 2D profiling at higher resolution is what we really need. We need to resolve 2D profiles on the scale of meters than what we have now, which is hundreds of meters. Please correct me if I'm wrong. I don't quite have that number in my head. But that's what we really need. That's the biggest problem with MSL, or one of the problems I think we have in terms of interpreting geology, is understanding what's going in subsurface. Is this layer, is this bedrock type overlying the layer, or is it abutting to it. It's really hard to tell sometimes. We get contradictory information from orbit, contradictory information from the MSL itself.
Okay, and that's it for this session. I think it's a 15-minute break, right? So we will pick up at 11:15, and thanks, guys, again.